Today's lecture is about elimination. This is a topic that I mentioned in the previous lecture in the context of solving equations in many variables, polynomial equations in many variables. So what is elimination? Okay, so this is the more general, fancier version of what we do in Gaussian elimination. So let's go back to the example that we discussed earlier about Gaussian elimination. This is for linear equations. Suppose this was the example that we had considered earlier. Suppose we have two equations. This equals 0 and 2x plus z minus 3 equals 0. So we want to solve these things. Common solutions. Okay. And by cancelling out the leading term, which is x in this case and also 2x in this case appropriately, we can get a third equation, and we saw this last time in an earlier lecture. Y plus half z plus 3 halves equals 0. Y plus half z plus half equals 0. Okay. Now this is the leading term. In other words, so ideal theoretically, what are we saying? We want to find, so we want to find v of x plus y plus z minus 1 and 2x plus z minus 3. Okay. So when we do this, we can find polynomials, or in this case linear polynomials, which do not involve x. So that is what we just said, that we want to find v of this, and on the way we found that any solution that every point above satisfies this new equation, y plus half z plus half equals 0. Okay. So how do we find this? So this is the question. Okay, so what we did, so how did we get this? So this we got by eliminating. This is what Gaussian elimination did. Eliminating x. Okay. So now how do we do, so what do we do in the general situation for arbitrary polynomials? So now we ask question. Okay, so how do we find such equations? In the linear case, we know we just do it by Gaussian elimination, which is clearing out the x terms. So how do we do it properly in the higher degree case? So I is a I is an ideal of R, which is a polynomial ring in some finitely many variables, x1 through xn. So this is a field as usual. Okay. And again, no assumption on the no assumption that it is algebraically closed. And S is the polynomial ring in one fewer variable. So in the earlier case, the linear equation case, it was x, y, z, and we leave out the first one and just ask for y, z. That's what we're doing here. Okay. And now we ask, what is the ideal? Okay, just one observation. This is really the contracted ideal. Okay, so this is really, so there is a S sitting inside R is a ring map. Okay, and I intersect S both in a set theoretic. So when you say S sits inside R as a ring map, so S is a subset of R and I is a subset of R, and this would mean the intersection of two subsets of R. This is also the contracted ideal of I. Okay. So what is this ideal? So that's the question. How do we determine this? Okay. So let's think about what sort of elements belong to I contracted to S. For all G in G, okay, for all G in G belongs to S if and only if the initial term with respect to lex of G is less than x1. Okay, so this is an observation that we would like to make, that if G belongs to S, then its leading initial term will not involve an x1, and that is precisely this condition that in the lexicographic order the initial term of G is less than x1. Okay, so we can use this. So what we do is, so we are going to describe a computational way to describe a way to compute this. So in other words, so we'll have to use some Grosvenor basis arguments, etc., and we will have to give this thing some monomial order. Okay, so give R the lexicographic order. So now what is the result? And yeah, okay. So theorem. Let G be a Grosvenor basis for I with respect to the lexicographic order. Okay. Then G intersect S. So now this is just an intersection really. Both are subsets of R and we just take an intersection, is a Grosvenor basis of I contracted to S, which is again, in this case, it is an intersection. So when you say Grosvenor basis of this thing, with respect to what? With respect to the lex order on S, which is the first variable is x2 now, then is x3, and so on up to xn. Okay. So we'll prove this in a minute. It's not a very difficult proof. So one observation that we can make is, well, if you compute the lexicographic order, the Grosvenor basis of I with respect to the lexicographic order on R, then we can compute this step by step, eliminate x1, then eliminate x1 and x2, eliminate x1, x2, x3, and so on. Okay, so just a remark here, that's before we prove it. Okay. Remark here, we can do this. So for all m less than or equal to n, okay, I contracted to the polynomial ring starting with xm to xn has Grosvenor basis. I mean, this is with notation as in the theorem, with G as in the theorem. Okay, has Grosvenor basis. G intersect k x1 xm through xn. So this is, one can recursively eliminate more and more variables from the beginning, this using lex. Okay. Now that observation we can prove the theorem. Okay. So note that G is inside I, so G intersect S is inside I intersect S. Okay. We want to show that, this is a generating set whose initial terms give the initial terms of the elements of that ideal. Okay. So let F be inside I intersect S. Okay. This implies that, so it's inside I, there exists a G inside G such that the initial term of G divides the initial term of F in R. Okay. But F is inside S. Okay. Notice that F is inside S, so x1 does not divide the initial term of F. Okay. R is UFD, which means that x1 does not, x1 is irreducible, x1 does not divide the initial term of G. Okay. So G is an element of S. This now implies that G is inside G. So we started off with an element inside G here, and now because of this condition it's inside S. Okay. So in other words, this is a Grobner basis. So remember, all these are considered with respect to lex. Okay. The only observation, I mean, if you really are picky, one should only observe that if you compute the initial term of F is inside S, if you compute the initial term of F, whether you think of it as an element of R or whether you think of it as an element of S, the initial term is the same. Okay, so similarly for G. So these are with respect to lex, and so hence we see that this is the proof. Okay, so therefore G intersect S is a Grobner basis of I intersect. Okay, that's the end of the proof. Okay. So now let's look at one example in Macaulay. So here is just ignore this all. Ignore all these lines in these examples. Yeah, so ignore that first line. The Macaulay code that we have input is this lines that are offset. R equals this, and we're defining it in monomial order. Then we're giving some ideal, x square plus y plus z minus 1, x plus y square plus z minus 1, x plus y plus z square minus 1. And then we ask for its Grobner basis. Then we ask for its generating set. And remember, in the previous examples, we have seen this as a matrix, but in order to make, to pick out the things that belong to the subring, we would like to just get it as a list. And this is the, you take entries, it will give a list of lists, and out of which you want to flatten it to one list, and so this is what we would get. Okay, so please look at the help pages of these commands, flatten, entries, to make sure that you understand what this is. Okay, so now here is the output. If you ask for flatten, entries, gens, so we ask for the ideal is this, x square, whatever we just put in, and this is just some long list which it cannot print in one line, so it just goes on. Okay, so that's the first line. So now we would like to select the elements of G that lie in the ring, in the ring where x is not there. So the tail of the variable, let's set y and z, that is eliminate x. And also in the ring z mod, so 101 is a prime number and z mod 101 is a field, and we would like to work with finite field at least to illustrate the examples because the computations are significantly faster. Okay, and that's the only reason. So we would like to eliminate x first here, and then y, x and y here. So that's what we want to do. So again, just ignore this line which says into. So this is just a header. Okay, so just you can, what you have to type into Macaulay is this line. So let's select is a command, and what it does is, so this is a function g. So this dash greater than denotes the maps to symbol in maths. So it is a function which we define without labeling the function. So it is just, so this is what we would write as a function. So g gets mapped to this thing. So we are defining a function on g, on the set, on the list g, capital G, and an element little g of that set gets mapped to, so this is the function, lead term of g is less than x. So this is a Boolean, I think this is either true or false. And what select command does is, it applies this function to every element of this list and picks out the one for which the answer here is true. So here it means that pick out all the ones in which the lead term involves only x, only z and y and z. Okay. And so it writes something out here. It's just again very long. So here is one with pure power of z, here is one with y square, and so on. Okay, so it gives us some list. So this is the elimination in eliminating x. Okay. If you ask for the second command, the same thing, we ask for lead term less than y, which means that the lead term, the initial term can involve only z, so it eliminates everything other than x and y, everything other than z, and here is what we get. Okay. So in fact, there is another command in so this is just to illustrate how lex works. One doesn't always need to use lex, one doesn't always need to use this approach. There is a command called eliminate in Macaulay directly, and the advantage of that command is that depending on the ideal, it can try to make some optimizations, okay, which on computing the Grosvenor basis, or maybe skipping some steps, etc. So there is a separate function, and it's probably better to use that. Okay. So let's just anyway compare it. Compare that our computation with lex agrees with the output of the eliminate command. Okay, so here we are just using the same I, okay, the one generated by those three polynomials. We ask eliminate xi, and then we ask show us the generators. That's because generators of, so if you just ask eliminate xy, it only showed us two generators. But actually, if you write out this code here, you will see that there are three things here. 1, 2, and 3, at least. Okay. I mean, and when you actually run it, you can count how many there are. So here, when we eliminate, we only get 2. But the reason is that it has shown us a minimal generating set and not the Grosvenor basis. So we can ask for its Grosvenor basis, gens GB, and it shows us those three polynomials. So this is in the lex order, when we selected everything less than x, this is what we would have got. Okay. And when you ask for eliminate, so now if you want to eliminate multiple variables, you have to give them as a list. Okay. And you can look at the help pages of these commands to see how they have to be invoked. Okay. So eliminate x comma y, the list comma I, it eliminates x and y and gives us this output. Okay. So that's the example about elimination. And as an application of this elimination, we want to discuss one problem that we have become familiar, one that we saw from the second lectures itself, if finding kernels of ring maps. Okay. So we will be able to do only a special case involving polynomial rings, but nonetheless it should give us an idea on how we can actually compute it. Okay. So what we want is, suppose let's say R is a polynomial ring, again over a field. This is a field, no assumption on algebraic closure, on some n variables. S is a polynomial ring in some different set of m variables, okay, and phi is a map from R to S, sending xi to keeping constants, keeping the elements of k fixed, xi's to gi's. So g1 through gn are elements of S. We would like to know the kernel of, what is kernel of phi? How would we compute kernel of phi? In the sense, how do we ask, well, if you ask Macaulay, it would compute, but let's try to understand one way of computing it using elimination. Okay, so let's define a bigger ring T, which is y, the y's and the x's, and we would like to think of this as in two different ways. We can think of it as R adjoin the y's and also as S adjoin the x's. Okay. Okay. So now let's define a ring homomorphism. Okay. From. Okay. So let phi tilde be the ring homomorphism from T to S, in which the xi variables go to gi's as it would have happened in R, and the yi variables are themselves are not changed. Okay. So this is a ring map. What is the kernel of this ring map? So let's, before we go ask the kernel, let's understand why we are interested in this. So we have R here, S, this is the map phi. Then we have T here and a map phi tilde. Okay. Now there is an inclusion map as a ring map. So let's call this map I for inclusion. Okay. So notice that if you take I and then apply phi tilde, this is same as phi. Okay. And kernel of phi is kernel of phi tilde contracted to R. So that's the reason why we would like to study this map instead of that. Okay. So now this gives us an idea that maybe there is some elimination involved inside here. Okay. So if you find the kernel of phi tilde, then we can eliminate the y variables and then we'll just get some ideal inside inside R. Okay. So let's try to understand what the kernel of phi tilde is. Okay. So T, remember, is S also, S adjoined the x's. Okay. And we have a map to S phi tilde in which xi goes to gi and elements of S are unchanged. Okay. So it would be an exercise, and this is something similar to that we did in the exercise, something that we did in the proof of Nullstellensatz, or a remark before the proof of Nullstellensatz, that kernel of phi tilde is kernel of phi tilde is generated by the set is generated by x1 minus g1 xn minus gn. Okay, so this is, one can prove it without much difficulty, and so there's an easy description of this kernel, and then we do an elimination. Remember, in the x variables first, we want to eliminate the y's. So when we order t, it should be ordered with the y's at the beginning and then the x's in the lexicographic order, and then we just apply this algorithm. Okay? So now let's try to do this. So here we have a map from R to S. R is a polynomial ring in 2 variables and S is a polynomial ring in 1 variable, and we define a map, x goes to t square, y goes to t cube, and this we have worked out earlier, the kernel is this. Okay. Now let's do it the way we had just described earlier. We put the y variables, the variables of S first, which is these things, and then the variables of the ring R, x and y, and then we just generate this ideal. We just formally write down x minus t square and y minus t cube. No thought has to be applied, depending on, okay, and then we just say eliminate t. Okay. So if you use this command, then we don't have to specify its Lex order, then Grosvenor base, etc. Just use this command directly, and it now says ideal x cube minus y square, x cube minus y square. Here it says ideal of R, here it says ideal of t. And there's some minor issue like this because elimination, in this situation, elimination is done in t itself, but one can safely ignore this part and think of it as an ideal of R. Okay. So that's the end of this lecture on elimination. From now, we will discuss a little bit more abstract things and develop more things related to, so we'll start off with modules and then proceed from there.